All right, let's start. Yeah, I don't know which marker to keep on using. I can't tell which of those is the most readable. Oh, let's try this blue one.
Go cross-eyed, the purple.
Purple's the worst.
I said if I go cross-eyed, the purple stands out the most.
Same.
Well, that's probably has to do with like there's only one line. Could be a psychological effect rather than the most readable when you have it on camera. Anyways, so today we're starting analytic geometry, and the geometry that we've been doing up till now is sometimes referred to as synthetic geometry or pure geometry. The difference is now we're going to introduce a coordinate system. So a little history about how this geometry came into being. It was, well, it's credited with being discovered by René Descartes. And a little history about him. René Descartes, he wasn't a very healthy person. He had very poor health. And so a consequence of that is he had to spend a significant amount of his time in bed. He had to sleep a lot. He would spend a lot of time sleeping. And he was also a great mathematician. He just didn't have as much time as his contemporaries to actually work on mathematics. And he found doing geometric proofs, the way that we've been doing geometry in this class, well, similar to, he had Euclid's axioms, not Hilbert's. He's way before Hilbert's time. He found it very, I think his verbiage is tiresome, or something to that effect. He was annoyed that you always had to, on these different proofs, come up with some clever trick to figure out how to prove this particular thing. So he thought it was really hard, took a lot of time to prove things, and so the story goes, he discovered analytic geometry to speed things up, make the proof simpler. So analytic geometry, in short, is introducing a coordinate system into our geometry. And the rule over of this is all over, especially in science. Physics, you both take physics, so this makes perfect sense to you. One of the first things we do when we start a physics problem is we pick a reference frame. And we set up our coordinate system starting somewhere. So if you got some ball launching through the air, we might pick where the ball starts as some type of origin. And then we talk about things in terms of that point. So that's instantly applying analytic geometry to the real world. You're applying Euclidean analytic geometry to the real world, to talk about that ball moving. So the side effects of this, or the uses of analytic geometry, they're everywhere. We can't get away from it. And it's very much, the way it's typically taught now isn't a separate course. It's usually introduced on a need basis. So when you take pre-calc and then calculus, they usually just sprinkle in the analytic geometry as you need it, and you keep on going. Because it's just, you need it. It's very hard to prove things without it. So that's a little bit of the history on there. So the first thing we need to figure out how to do is add coordinates. And the simplest thing to add coordinates to is a line. So we're going to start out by talking about the coordination of a line. When we talk about this, we're going to talk about distance. And so I just wanted to reintroduce the idea of absolute value. The absolute value of x, one of the ways that you can define it is the absolute value of x if x is greater than or equal to 0. And then the absolute value is negative x if x is less than 0. So the absolute value of negative 2 is negative 2. Or in other words, 2. Right?
Mm-hmm.
Negative 2 is less than 0, so apply the negative to it. So negative 2. And then the absolute value of 3 is greater than or equal to 0, so it's just 3. That make sense?
Yeah.
So that's another way that we can define the absolute value function, because we're going to introduce it a little bit here as we go. So the coordination of a line, how do we do it? So what we need to start out with, and you've done this anytime you've drawn an axis on a piece of paper, you start out with some line. That is just garbage worthy how bad that is. hopefully nothing's worse. You start out with some line L, and you start out with some unit length. I'm going to call that a unit. And then you pick some point on the line, doesn't matter where, we're going to pick the center for the sake of convenience so we can go both ways. And you call that O, and we refer to that as the origin. And then we pick a point on a side of the line, doesn't matter which side. As a matter of convention, we pick the right side. And we call it P1. Maybe this way some. P1, and we choose that point so that that length is 1 unit. So we select a point P1 on a particular side of L such that the segment OP1 has length 1. And that's what you do when you do it. You start out by drawing a line, you draw the point for your origin, and then you arbitrarily decide what you're going to call 1 unit length, and you start making your tick marks of 1, 2, 3, 4. So you've done this a ton of times. So, as just to name things, the side of L containing the point P1 we call the positive axis or the positive direction, and then the other side is referred to as the negative axis or the negative direction. Common terminology that you've probably heard before. So, anyways, then for each positive real number, that's a for all symbol, for all numbers in the positive real numbers, the symbol R is a set of all real numbers. When we put that plus there, we're saying we're just talking about the positive ones.
Okay.
So that is a short way of writing for all positive real numbers. There exists a point, we'll call it Px, on the positive axis such that the length from O to Px is x, which is also the absolute value of x. So pick any positive real number, we're going to call it x. We're saying there's a point that we can find on this line, Px, such that the distance from here to here is x. Okay?
Okay.
And we get that from the completeness axiom. If you remember, it was introduced in this class what was called the Archimedean, I don't know if they called it the Archimedean axiom. But the completeness axiom said, for any real number, you can find a point such that the distance from a particular point to that point is that real number. So if I have a line, I pick a point on the line, then for any real number, I can find a point on a particular side of the line such that the distance to that line is my real number. Oh, and also given some unit length. And then the Archimedean principle was the other way. For any point, I can find a number. Archimedean said for any point I can find a number. Completeness axiom said for any number I can find a point. Okay? And those were two axioms way, way back. But they were the last two axioms that we introduced for our planar geometry. Anyways.
So does analytic geometry use all of the postulates from...
Everything that was true in planar geometry is still true in analytic geometry.
Okay.
We're taking planar geometry and now we're adding a coordinate system. And that gives us analytic geometry. And so that's one of the powers of it is sometimes it's easier to prove things one way, sometimes it's easier to prove things another way. And so you go back and forth as needed for whatever it is that you're doing. Okay. So, there's our picture so far. We also say that for all x prime in the negative real numbers, there exists a point Px prime on the negative axis such that the distance is equal to negative x prime, which is also the absolute value of x. Remember, x prime is a negative number. So for any negative number you pick, I can find a point over here. So for any negative number you pick, x prime, I can find a point on the negative axis called Px prime, such that the distance from here to here is negative x prime. Or that's also the absolute value of x prime. Same thing. And this is also the absolute value of x. right?
Right, okay.
And then a side note, oh, sorry. I kind of ran out of space right here, but I'll just say it out loud. We call that x and that x prime the coordinate of that point. So the coordinate of a point is
the number.
that particular number. X is the coordinate of this point, px. X prime is the coordinate of this point, x prime. So the coordinate of p1 is 1. The coordinate of px is some positive number x. The coordinate of px prime is some negative number x prime. So that's our definition of coordinate. Okay? So now we've taken a line and we've added coordinates to the line. That's what we mean by a coordinate. All that makes sense so far?
Mm-hmm.
Okay. Now, we're going to make 2 of them so we can talk about the plane. Now, that's definitely someone on the roof.
No, it's a cannon.
Huh?
It's a cannon.
It's a Kim?
A cannon.
Oh, a cannon. Yeah, cannon. Alright, so now let's talk about doing this with 2 lines. So when we want to when we want the coordination of an entire plane, how do we do that?
2 lines perpendicular.
We pick, yeah, exactly. We pick some point O. We have our unit length in mind. That's 1. And then we draw 2 perpendicular lines through that thing. There we go. 2 perpendicular lines through that thing. And then we coordinate. We coordinize each of these lines.
Coordinate.
Yeah, that's not bad. You have the coordination of each of these lines,
Coordinate.
which is exactly like adding our tick marks onto particular points, right? So we marked some particular points to help us talk about things easily. This is P1, P2, P3, P4. And so we'll say that we happen to choose this one to be the positive axis of that one and that one to be the positive axis of that one. Just arbitrarily.
Okay.
Now, there's no reason on planet Earth that these things have to be pointed in a particular direction. Well, before we talk about that,
Right enough.
we should also mention, huh?
You're saying they don't have to be pointed.
Yeah. So, before I talk about that, one more thing. You pick one of these things, we need to distinguish the 2 different axes, right? So one of them, you pick, doesn't matter which one, and we call it the abscissas. So we'll pick this one, and this one is the abscissas. So the set of all points inside of here, it's the coordinates. The coordinates of each of these points are referred to as the abscissas. And then the coordinates of each of these points are referred to as the ordinates. Why those names? I don't have a clue on planet Earth.
And you pick them arbitrarily.
Doesn't matter which one you pick to be which. Now,
Do they have different implications? Like this means this means this?
what do you mean this means?
So when you say this is the abscissa, does it have like some other requirement for that?
No, you just pick one of them, and I'm going to call all the coordinates for this line, the abscissas, and I'm going to call all the coordinates for this line, the ordinates.
Okay.
Okay? So right here we have coordinate 1. Right here we have abscissa 1.
Okay.
Okay? Now, as a matter of convention, we orient our graph, shouldn't say graph, we orient our coordination so that the abscissas point to the right and the ordinates point up.
Here.
We usually use x's to signify the abscissas, and we usually use y's to signify the ordinates. And so this is sometimes also referred to as the x-axis, and this is also sometimes referred to as the y-axis. And the entire plane, once it's been coordinized, is referred to as the xy plane. Right? So when we're talking about abscissas, we're talking about the thing that you've typically designated with an x. And when we talk about ordinates, we're talking about the things that you've typically designated with a y. I don't remember pushing record on this.
It's going.
It's going. Just from that one time. Going to be a little bit paranoid now from here on out. Okay. So, now we can talk about the quadrants. And let's draw a picture again so that we have the abscissas pointing to the right, so that the positive direction of the abscissas is right and the positive direction of the ordinates is up. So we'll redraw it. Here's our abscissas, and then the arrow I just put on to point, show which way is considered my positive. And then here's my ordinates. And then we'll say that that's a unit length 1, so 2, 3, 4, 5, whatever. Doesn't matter.
We're going to start labeling all my graphs A1, A2, A3, and O1, O2, O3.
Well, we typically use O to mark the origin, so that would be confusing.
Well, O's in the ordinate.
I know where you got it. Yeah, it's terrible naming, and I think that this somehow means first, and this somehow means second. So whichever one you coordinate first is your first one, and we'll call all those coordinates the abscissas, and the second one that you coordinate we'll call the ordinates. Anyways, that's that. Oh, what was I talking about?
Is now on it.
The quadrants.
Is now on it.
Oh yeah, what's his now?
This is not a fortunately chosen word.
Yeah. Yeah, it is not a fortunately chosen word. And it's actually more modern textbooks, they kind of just briefly mention that as a side note, and then they kind of drop it out of the rest of the text and never say it again. But if you get older textbooks, they use this terminology a lot more. Like the calculus textbook we're using always talks about abscissas and ordinates. It doesn't talk about the x-coordinate axis and the y-coordinate axis. Or x-axis and y-axis. Anyways, so we can now talk about the quadrants of our plane once we've added these coordinate lines. So we call this way the positive and this way the positive, right? So we call everything that is on the same side of this line as this positive axis, and the same side of this line as this positive axis. We call that quadrant 1. And then the one that's on the positive side of the ordinate, but the negative side of the abscissas, we call quadrant 2. The one that's on the negative side of the ordinates and the negative side of the abscissas, we call quadrant 3. And then the one that's on the negative side of the coordinates and the positive side of the abscissa, we call quadrant 4. Name of quadrants. The first theorem in the book is just a special case of one that we've already done. So the one that we already did, I'll remind you of it. We said that if we had some angle, if you took the lines that extended them, then if I had a point here and a point here, then there was a point on this angle between them. If I had a point here and a point here, there was a point on this angle between them. And if I had a point here and a point here, there was a point on this angle between them. The first theorem we have over here is if you have 2 points in the same quadrant, Oh, and we also had, if we had a point here and a point here, then there's no point on the angle between them. Okay? So the first theorem says, if you have 2 points in the same quadrant, there's no point on either of the coordinate lines between them, which is just a special case of this. Right? And then it says, if you have them in different quadrants, then there is a point on the axis between them. And we know that there is because not only is there one, but there's one on this actual angle right here. No matter where I put this other point, there's going to be a point on this angle, this 90-degree angle, between them. So it's just a special case of this theorem. He doesn't reference this theorem in the proof, and he re-goes through it, but it's just a special case of what we already did. So maybe this was a homework problem that we took the time to go over in class, and that's why he doesn't. But he doesn't reference that theorem for some reason. Anyway, so we already have that. So 2 points in the same quadrant, then there's no point on the axes that lies between them. And then if they're on different quadrants, then there is a point on the axes that lie between them. Not a very interesting one, but it is what it is. Oh, I didn't talk about the planes.
Is it a requirement that they're perpendicular, perfectly perpendicular, or could they be?
Start definition.
It was required for how we are developing analytic geometry. You'll find out, if you haven't already, that sometimes it's useful to coordinate it differently. One way to do it is, for example, polar coordinates. Now, we haven't talked about giving coordinates to a point out here yet. The only things that have coordinates so far are points on the abscissa, or points on the x-axis, and points on the y-axis. We have our abscissas and we have our ordinates. Those are the only coordinates that we have so far. So we haven't talked about how to get that point of coordinate yet. But once we do, then there are other ways of assigning coordinates to things other than this one. But for this one, yes, we require that these two lines be perpendicular and going through O. More definition, we call the plane on this side of the ordinates, on the same side of the ordinates as the positive abscissas, the right half plane. So from this line over, we call this the right half plane. We call everything over here the left half plane. We call everything up here the top half plane, and we call everything down here the bottom half plane. So that gives us kind of a preferred orientation for how this graph should be laid out, which is as we've done. And then I think they actually define the quadrants in terms of the half planes rather than the sides of the line, but it's logically equivalent. It doesn't matter how you do it. You'll get the same thing. Okay, so now let's talk about giving coordinates to some point. So now I pick some point out here. Pick some point P. And then I construct two, maybe offset it because I need to construct two lines through P. I construct a line through P, I'll call it L1. I'm not sure if I'm doing this the same as the author, so. I construct L1 through P, actually I bet you he calls this one L2. So I construct L2 through P so that it's parallel to the x-axis. And I construct L1 through P so that it's parallel to the y-axis. Then I define the coordinates of P to be the abscissa of this point and the ordinate of this point. Does that make sense? So if this point was Px and this point was Py, now the coordinates of P are x, y. let me read his definition exactly to make sure I didn't miss anything. Let P be any point of the plane, and let L1 and L2, the lines through P, parallel, respectively, to the axis of ordinates and the axis of abscissas. So L1 is parallel to the axis of ordinates, and L2 is parallel to the axis of abscissas, so I did the same. The line L1 meets the first axis in a point A, we call it PX, and meet with coordinate X. The line L2 meets the second axis in a point B, we call it PY, with coordinate Y. The two numbers x, y are called the coordinates of P. We write them in parentheses, x comma y, and refer to that x comma y as a point. The number x is the abscissa of P, and the number y is the ordinate of P. So that's the full definition. So we call x the abscissa, we call y the ordinate, that way we know the order that they go in. Because x comma y is not the same thing as y comma x. Those could refer to very different points. Good?
There's nothing keeping our coordinates to whole numbers of our units, is there? Because of that one proof.
It's not a proof. It is the completeness axiom. The completeness.
Right. I can say for my origin in a given number, I can find that point, right?
Two of them is what it says.
Right.
A point on either side.
Either side.
Yes.
So I give you pi, and you can find.
I can find a point on either side of this such that the distance from here to that point is pi.
Pi.
And pi we would call the coordinate of that point.
Pi. But you have to be talking about a certain unit when you use that axiom, right?
Yeah.
Okay.
That many units away.
Okay. Next.
Because you can't talk about distance unless you have a unit. It doesn't make sense to say that's pi away. It needs to be pi inches or pi feet or pi something. Pi of some unit. So yeah, that's what that axiom gave us. Okay, so that's how we...
Here is the other axiom. It's not the complete list. Pythagorean axiom.
The Archimedean, it's usually referred to as the Archimedean principle, or at least that's the way I've happened to hear it the most, because it's something that you can prove.
Using the completeness axiom.
No, it's something you can prove in general. In short, what it's saying is that there's no greatest natural number. Now, maybe you could use that as an axiom instead of some other axiom, but it's not something that falls from the completeness axiom. Like in our calculus book, as we go through it, we're going to prove the Archimedean principle before we ever talk about the completeness axiom. So anyways, this is how we assign coordinates to points. Now, we give it an abscissa, which comes from this line, and we give it an ordinate, which comes from this line. And so the great power of this is now we have assigned numbers to points. I guess I want to talk about lines first. I thought we were going to start talking about distances. Maybe do a side note about distances real quick, then we'll talk about lines. So when we're talking about the distance from the origin to a point, we already know what that is. It's just the coordinate, right? That's how we define the coordinate. It's either its distance to the origin, it's the absolute value of its coordinate, sorry.
Okay.
The absolute value of the coordinate gives you its distance to the origin. So now what about if I have my origin right here, this is x1, and this is x2. How do I find this distance? The distance between x1 and x2.
X2 to the origin minus
Right, I
x1 to the origin.
can take, maybe instead of calling it that, let's say that this is P of x2, and this is point of x1. That's what those points are. So then this distance is this whole distance minus this distance. Or sorry,
The other way, so it's.
this whole distance minus this distance gives you this distance.
Right.
So it's x2 minus x1,
Absolute value.
absolute value.
Wait, yeah, but also absolute value each of those.
Also, absolute value of each of those. Yeah. Either way works fine. Does either way work fine?
Has to be, because the distance is defined as the absolute value of the order.
Because then you have to order it right if you do that.
Yeah.
So you need to put the absolute value around the whole thing.
Well, I'm saying both. You've gotta include both the absolute values around the variables and the whole thing.
Okay. So we won't do it as a proof,
Yeah,
but
6 straight.
the absolute value of the absolute value of is that just equal to the absolute value of x minus y?
X is -2, y is 3, -6, +6. -6, +6. X is 2, y is -3.
So let's take an example of a
Negative
negative number
one.
and getting the difference between those two.
+5. See, it's not the same.
Yeah, I'm pretty sure that this is right. x2 minus x1 absolute value.
Why?
Because
Yeah, absolute
x2 minus x1 in general,
value gives us another coordinate.
x2 minus x1 gives you that distance when you have it ordered the right way, but it could also give you the negative of that distance if you ordered it this way.
Right.
Now you did that distance minus that distance. Oops, now you did that distance minus that distance, which gives you the negative of it. So that makes it always right. Right?
Yeah.
Because distance always has to be positive.
Right, okay.
So, put the coordinates in there, take their difference, absolute value, you don't have to worry about the order. So that's how you find distance on just a line. Now, we haven't talked about how to find distance when the 2 points aren't on a line. But before we do that, the author wants to talk about lines and equations of lines. Okay. Straight lines. Having coordinates, we naturally ask how lines may be described by coordinates. In the exercises, we have already examined a few lines. For example, the set of all points. Okay, so now we want to capture the idea of lines in this geometry. So start with simple cases. We'll start with lines parallel to our axes. If this is some point A, and I have a line that goes through here, so I have that line, but this line is parallel to this line, then by definition, all the points on this line have the same abscissa. Right? How do I get the abscissa of this point? I draw the line through it parallel to here. Wherever it meets, whatever point it meets down here, I take its coordinate, and that becomes its abscissa. So all these points have the exact same abscissa, every point on this line. The abscissa we usually represent with x, and the ordinate we usually represent with y. So to represent this entire line, we have the equation x equals a. That's the equation that we use to represent the line with all their abscissas equal to a. Similarly, if this is a point B, and I have a line that goes through a point with coordinate B, with ordinate B. So if I have a line that goes through there, then every point on this line's ordinate is going to equal B, by definition of how we do that. So we can represent this line with y equals B. We typically use y to represent the ordinate, and we typically use x to represent the abscissa. So for parallel lines, it's simple enough. We now have a way of capturing a particular line parallel to the ordinate, and we have a way of capturing a particular line parallel to the abscissas. So those are special cases, but we want to capture a line in general. And then the author wants to go through a little example first, which I think we're already all familiar with, stuff like it. We can just make up our own. So if I have 2y equals 4x plus 3, we are all already familiar with the fact that this somehow represents a line, right? And so the author goes through the exercise of, you can pick any abscissa you want, completeness axiom, and then every time you get an abscissa, every time you pick an abscissa, you'll get an ordinate. And so if we take the set of points that satisfy this equation, who 4 times their abscissa plus 3 equals 2 times their ordinate, then we end up with a line, right? And let's see, what's that line going to be? It's going to be roughly, it's going to go through at 3 halves, and it's going to have a slope of 2, right?
Mm-hmm.
So it's going to be roughly, blue, really roughly this line. That's a line. So there's a really rough picture of what that line might look like, and all the points that we went and plotted, we find that they come somewhere on that line. So it's real tempting to think that every line can be somehow represented with an equation like this, and every equation like this somehow represents a line. And we know that that's true from our experience with math, but that's something that we need to prove. And these types of equations that represent lines, we refer to as linear equations. For example, you may already know, have in your head what something like this looks like. Parabola, which is not a line. So this is not a linear equation. This is a linear equation. That's where linear gets its name. It represents a line in some sort of analytic geometry.
What do you call an x cubed line?
You don't call that a line?
Cubic. This is not a line.
It's a quadratic equation.
This is a parabola. It's a curve, and it's still a curve. Curve is our general name for all of them.
Huh.
The reason it's not a line, we know right out the door. A line has to satisfy the...
Intersecting, it's 2 points.
Huh?
Another line intersecting it can hit 2 points.
Oh yeah, there you go. That's an easier check than what I was going to do. I was going to use the betweenness postulate. But that's easier. Yeah, you got something that's not that, intersecting that at 2 points. So no, that's not a line. You know what it looks like, right? A U?
Mm-hmm.
Yeah. Okay. So now let's prove our theorem. So the theorem is this. I probably should have left that. Picture is going to help. I'm not sure which way we're going first.
A, B, and C are given numbers. Am I on there wrong?
Then the equation line, that lies on a single line. So we're showing that all the points that satisfy the equation lie on a single line. That's the first way we're doing it. Yeah, you're on the right one. So basically what we're saying is, if I have, is it AX plus BY plus C, or plus C equals 0?
Yeah.
So if I have an equation of this form, then all the points who satisfy this equation lie on some line with one requirement. We require either A or B is not 0. Notice if A and B is 0, and if C wasn't 0, then you've got something that doesn't make sense. So we require, for this to be the case, that either A or B is not 0. And we'll prove it in each of those cases. But it also helps to have a picture to talk about. Maybe I'll do a picture over here. Purple worked okay. Let's see if it works again. Let's see, which cases you start with?
A equals 0.
Yeah, we'll get the two parallel lines in those cases. So, case 1. Case 1, A equals 0. If A equals 0, then by equals negative C, or y equals negative C over B. Right?
And it's just all the points with that.
And we already know what that is. That is the line parallel to the abscissas going through the ordinate negative C over B. This is a number since B is not 0. We required either A or B is not 0. Case 2 is the exact same. Case 2, we have B equal to 0, and so we get x is equal to negative C over A. Which, once again, we've already talked about those lines. So case 3 is the one that's interesting. So case 3, both of them aren't 0. Case 3, A is not equal to 0, and B is not equal to 0. And I guess he picks two arbitrary points. Yeah. So we need to show that this equation still gives us a line. All the points that satisfy this thing are points on the same line. And are points on a line that goes through this point, right?
Yeah, but I don't know why.
Why it goes through this point?
Yeah.
Because it has to have a coordinate x, or it has to have an abscissa of 0.
Okay.
Has to satisfy that. And so y equals this is something that has to be satisfied. Yeah, the y-intercept, in short. So we're going to show that everything on here is satisfied, or is on a line that goes through here. Now we'll take a line that goes through here, we'll pick a particular point, that will give us our line, and then we'll take another point and show it's also on that same line. So we need 2 points to define a line. So I'm going to pick 2 points on here, I'm going to pick this point and some other point, and then I'm going to take some other third point that satisfies that thing and show it's also on the line. You see how I need 2 to get my line first and I go from there?
Mm-hmm.
So I'm going to pick the point x1, y1, and x2, y2. We'll say x1, y1 is on the line, and then we'll show x2, y2 is also on the line. So we'll start with our picture, and then I'll go back over there to drawing. So let me just, here's maybe more of a slope. Will help me draw. There it is. So we've got x1, y1 we know is on there. x1, y1, hopefully you can read that. And then we need to show that x2 y2 is also on there. Okay? And then let me just label some points. This is a point 0, comma, negative c over b. This is the point x1 comma negative c over b, and then this is a point x2 comma negative c over b. Drawing this line parallel to this line. And then we know that this is a right angle and this is a right angle because the line that I used to get this thing's coordinate is the line parallel to this, and a line parallel to a parallel is perpendicular. Similarly with that. Okay. We need to use the fact that we know that this point and this point satisfy this equation. Okay? So plugging in x1, y1 to this equation and then solving for y1, we're going to get, let's see, by1 equals negative ax1 minus c, right? So y1 equals negative ax1 minus c over b. Did I do that right?
Yeah.
Y1 equals negative ax1 minus c all over b. And similarly, y2 is going to equal negative ax2 minus c over b. Oh, sorry, I lied to you before. We're taking the line through this point and this point, and we're taking the line through this point and this point, and we're going to show that those are the same lines. Those two lines coincide. That's what we're doing. And the way that we're going to show that those two lines coincide is that this angle is the same for both of them. And the way that we're going to show that that angle is the same for both of them is we're going to show that this big triangle is similar to this small triangle. You follow that logic? So take the line that goes through this point and this point. Take the line that goes through this point and this point. You have two lines. Make this right triangle, make this right triangle. Now those triangles don't necessarily coincide, right? This point could have been down here and that goes like that, and this point's up here and that goes like that. We know ultimately they do coincide, but that's not given. So we take those two lines and we construct these triangles with each of those lines. If I can show that this triangle is similar to this triangle, then I know that those angles are congruent on them, and therefore it's the same line that goes through those points. Does that make sense?
Yep.
Because there's only one line I can use to make a particular angle from a particular ray. So here's the ray I'm going to use. There's only one line I can pick on that side such that I can get my angle. So that forces them to be the same line if I can show that that angle is the same for this triangle and this triangle, which we get by showing that they're similar. Okay, so to show that they're similar, I need to show that the ratio of this distance to this distance is equal to the ratio of this distance to this distance. Right?
Yeah, but couldn't you do it with the other side too? It doesn't.
The ratio of this distance to this distance?
Yeah.
We haven't talked about distance when our lines aren't parallels.
Oh, okay.
So I know how to talk about distance here, I know how to talk about distance here, I don't know how to talk about distance here yet.
Okay.
So we don't have that yet. So, let's see. What is this distance? This distance is y2.
Minus 4 plus. Yeah.
Y2 plus CB. So that distance over Y1 plus CB. Let's see. What does that equal? How can we simplify that? Well, this is, oh, we could probably just construct that, right?
Oh, that equals each other. Okay, I see how that works. Those equations are identical except for the x2 and x1. So once you plug in,
Right, that's going to give me the.
so x2 over
Oh,
So you're getting
really
the
quick.
ratio.
Oh, let me write out this equation now.
Yeah,
Because that's what I want to show it's equal to.
the ratio of it.
So the ratio of. So what's this? This is just x2
X2.
and this is just x1. So I want this to equal x2, x1. y2 we know is this, right?
Yep.
So we've got negative a x2 over b minus c over b plus c over b.
Cool.
So that's just going to be
minus
negative a over b x2, x2 not x squared. And similarly, this is going to be negative a over b x1, right? And then the negative a's over b cancel out, which is x2 over x1, which is the ratio of this distance to this distance, right? So those triangles are similar, so that angle is the same for both triangles. So it's the same line. So we just barely showed for any equation of this form you pick, as long as one of those isn't 0, it corresponds to a line. And hence we call all equations of this form linear equations. And that's called the general form of a line. There is another useful note to put in here, but where do I want to put it in at? I'm sure the author made it somewhere.
And no, like.
Oh, yeah, it's going
X1
to come from the next theorem. That's all we have for that. Huh? Check my battery real quick. Oh, it doesn't show me yet. Jump.
Even if you tap it,
Shit.
I won't pause it.
we'll tap it away from the pause button.
I don't know.
Won't it wake up and hold it in there?
No, doesn't show me. That's done. All right, next theorem. If L is a line, then there are numbers a, b, and c with not both a and b 0, such that every point x, y on L has coordinates that satisfy the equation ax plus by equals c. Right, so we showed for any equation you pick, we can find a line. Now we need to say for any line you pick, we can find an equation. And then there's a one-to-one correspondence between these equations and these lines. And so then we can use equations to represent lines and lines to represent equations. Right? So let's do it the other way now.